Okay, I think we should get started. Hello, everyone, and thank you all very much for joining us. My name is Alex Rosenthal, and welcome to the 8th in the In Control webinar series presented by Live Rieger. Live is the CEO of In Control Solutions and specializes in instrumentation, monitoring, modeling, and control of water resource recovery facilities. A focus of his work is to develop new tools for data quality evaluation to more effectively optimize treatment processes. Live has been a leader in our field for many years. He was the founding chair of the IWA Task Group on Good Modeling Practice and was the past chair of the Water Environment Federation Modeling Expert Group of the Americas. Before we begin, I have a couple of announcements and requests. First, we are recording this webinar and will post Live's presentation to our YouTube channel. Our previous webinars are already available on YouTube, and we welcome you to view them and contact us with any questions or feedback. Second, we ask that you all mute your microphones and turn off your cameras to ensure the best possible audio and visual experience during the presentation. And finally, we plan to reserve time for questions and answers at the end of Live's presentation. What we encourage you to do is to write your questions into the chat window at any time, and we'll do our best to answer them during the designated question and answer session. So the title of the talk, Controls Are Supposed to Work, Right? Is a terrifying rhetorical question that many of us ask ourselves. And I think I can speak for everyone here that we are very fortunate to have Live present on the key considerations to successfully deploy control systems at water resource recovery facilities. So without further delay, I'll hand things over to our friend and colleague, Live Rieger.
Thanks, Alex, for your intro. Yeah, so I have a challenge today.
录也可以吗？我用 G 还是 G 是吧？
Okay, so please mute your microphone. Okay, so I have the challenge today to give an overview of control fundamentals and keep that short. I try my best. It's clearly not really easy to explain all that, which is very often just a sideline in the studies we do, but very important, right? So I specialize quite a bit in process control. What I see right now is that there's a lot of talk on doing different types of control, using machine learning or even artificial intelligence, also using digital twins, but hardly ever can I see that somebody really analyzed what is wrong with the control system and then tries to overcome it. Yeah, and I think that is something we really have to do in our industry. If we properly understand what is wrong, then we can overcome it. But too often, actually, I think we are ignoring the underlying fundamentals. So that's the reason that I thought, well, go back to fundamentals and try to outline a couple of things impacting control performance. Yeah. Okay, so a little bit on In Control Solutions. We focus on providing smart digital solutions in wastewater, that is collection and treatment, and also waste management, and try to use our different skill sets. So we are a very strong team with different skill sets ranging from instrumentation, monitoring, control, but also things like modeling and simulation, of course, and we do more and more data-driven modeling as well. Yeah, and in the end, we want to encapsulate all that in our software. Yeah, so what we provide is very strong focus on data because we believe that the solid data foundation is really key to any engineering work. Yeah. With respect to today's webinar, control system design based on process and equipment insights is very, very important. We developed the models to look deeper into these systems. There were a couple of webinars already on ration system modeling and also on other aspects of our work. I would strongly recommend to have a look at our YouTube channel and see some of our other webinars. So really the key for us is to translate our in-depth understanding and our expertise into software which is helping operators to get to better performing plants, right? So we really target operators and not just some engineers who may be able to figure out tricky questions themselves. Yeah. Software products, you may know our simulation platform, Simba. We are resellers of Simba, developed at IFAC in Germany. Our own products are rolling out right now. So that is Ops Control, our online monitoring and control platform. So we do both monitoring and control solutions in that platform. And then we have another offline platform for data management and advanced analytics. With that, let's jump into today's webinar. Quick outline, I start with control fundamentals, but then really want to discuss control system design. So that is describing what we do if we get a control project, how we approach that, and how we basically discuss with the clients to come up with the best solution, taking limitations into account. Then a little bit about commissioning and operation, and then of course the take-home message. So let's talk a little bit about control fundamentals. First, some basic structures. What you see here is a feedback controller. So on the left-hand side, you have a set point. This is what you actually want to maintain. And on the right-hand side, you have the target variable, and that is what we often call controlled variable. Yeah, and then the controller is called, named typically after the controlled variable. The controlled variable is measured, and then it goes back, and then you compare what you measure in reality versus the set point, and that is called the error. And then there are certain equations applied to calculate what the controller should do, right? So, and should do means varying a final control element, so a motor for a valve, for example, or a VFD to change pump or blower speed and the like. Yeah, and then you have the process. So the essential point here I want to make is a feedback controller relies on the process response. Yeah, so that's very important to understand because the process itself doesn't have to be fully understood. Very important in terms of how to set up that control and what that controller can do. So the other thing often discussed, and you see that more and more pitched to clients or to utilities, is a feed-forward controller. So I refuse to put only feed-forward in here because I believe you always have to do that with a feedback portion, right? So that could be a feedback trim like described here, or it could be that you have some feedback signal you use to auto-calibrate your feed-forward model. Yeah. So the main difference here is that instead of measuring the controller, the process output, you are measuring the disturbance, right? So the disturbance changes the process. Yeah. So it should be clear that this is allowing you to react very early on. Yeah. So you still need a measuring device, but then you need some kind of a model. And that is very important to understand that need for a model. And you know, the more complex, the more accurate maybe the model is, but then also the more sensors you need, right? So that feed-forward model can be very simple, but keep in mind, you are not measuring what the process is doing. You are estimating or predicting what the process is supposed to do. Yeah, little example, if you are predicting nitrification, so you're measuring ammonia before the process, you need to predict what the process can remove in terms of ammonia. If you have some inhibition in your influent, that model will not know that typically. Yeah, so you have to put safety margins around, and therefore I would say you always need a feedback setup. Okay, so the positive side, the advantage is clearly very fast reaction before the disturbance hits the process even, right? So depending how you set that up. So that is required in certain situations, but you buy that by the requirement to have a process model, which means typically as an engineer, you put additional safety margins around. Yeah, so I would say you should always have a feedback signal attached to it. In my experience, for most wastewater applications, feedback control is sufficient, right? So clearly check if you really need feed-forward control, then it's fine. But if you can do feedback only, that is the much more robust solution, and I would recommend to keep it simple. Okay, so these slides I borrowed from Manel, another InControl team member. So I try to do that without any equation, right? So that's also quite a challenge for an engineer, but let's give it a try, right? So what we have, again, so on the left-hand side, that's the set point. We have the controlled variable. We measure something, calculate the error, and then basically we apply a proportional, integral, or derivative part. The outcome, so the controller output is what we call the manipulated variable, and that goes typically on a controlling element, right? So in this case, we are changing the valve position. So the question now is, how do we set that manipulated variable so that we maintain the controlled variable around the set point, right? And you already see these three things are essential, and this is what you check if you want to look into controller performance, right? So the proportional part, that is the present, what is happening right now. So that is basically a factor applied to the error. Yeah. Then we have the integral, that is the past, and I will try to explain why you need that. And then you have the derivative term, which looks kind of into the future, right? So it looks at the rate of change, allowing a faster reaction. Okay, so let's look into proportional controller. So only using the proportional part, right? So you have the DO set point, and then you measure the DO, and basically what you then do is you calculate the error, right? So in this example, set point is 2, DO measured is 1, so the error is 1. Yeah. So then you apply a factor. In this case, the gain is 0.05. That's just a simple example, right? And the gain also translates from the unit of the set point and the controlled variable, so what you measure. So they have, of course, the same unit. You translate that into the unit of the manipulated variable. So that is important as well. So you are including that unit conversion in there as well. So in this case, with that gain, the valve position would be 50% open. Yeah. So basically what that means is the larger the error, the more air is required, right? And if the error is getting smaller, so in this case over time, the error gets smaller, so the valve position should get more and more closed as well. Yeah, so That is, I would say, relatively straightforward. The gain here, examples of what is happening if you apply a larger gain, so then the reaction is faster, and a lower gain, probably a little bit more time to actually get to the set point. Yeah, so that's all very steady state thinking here. Okay, so another example, let's say you have a DO set point of 2, but this time you actually, you are at the set point, right? So set point 2 and measured 2 as well. So what is happening with our calculation? 2 minus 2 is 0. Oh, what is happening now? So the P control, the proportional controller, would still apply a gain, but 0 times something is still 0. That means you close the valve, right? And that doesn't sound like a good idea, right? So you should always provide some air to the process, right? So you would not just stop it. So this is called a steady state error. So two solutions to that. One is if you do a proportional controller only, you can introduce a bias, right? So basically you decide on average you need so much air, and then the P controller just works around the set point. Yeah. So this is one option, but then you have to set that bias term manually, right? So that's something you have to watch and adjust. The other way is that you actually add an integral term. So the integral term looks into the past. It accumulates the error over time, so or integrates the error over time. Yeah. So this is now a PI controller, and basically to highlight that the item keeps a running total of the error over time, right? So depending in which direction the error goes, that accumulated portion, that integral portion, goes up and down and can also get negative, of course. Okay, so let's see what's happening. So you see that there is a little bit of overshooting here. And what you can do is if you add a derivative part, then you look into the rate of change. And then typically, if you have a, let's say, a smooth input signal, so the controlled variable signal, what you measure, then you smoothen it out, and hopefully you can closely maintain your set point. In wastewater treatment, be very careful with controllers trying to maintain a fast changing variable. So for example, in DO control, the DO signal is changing so fast that the derivative part may amplify the noise you have in that signal, right? So you have to be very careful. Typically, in wastewater treatment, you use a PI controller, and the D part you reserve for something which is a bit smoother. For example, if you do ammonia-based, you can put a D part on the ammonia controller. Yeah, just to mention that. Okay. So let's get to something that should be part of your curriculum. So I hope you heard everything on PI controllers. This one is something which I find that it is often overlooked, right? So this is basically how we ask everyone to look at controller performance, right? So before you apply any metrics or key performance indicators, this is what you should do first. Very simple. On the left-hand side, you plot the set point and the controlled variable. They have the same unit. In this case, it's the DO controller. And on the right-hand side, you plot the manipulated variable, which often has a different unit. Yeah, or most of the time has a different unit. What you also need to plot are the controller bounds, right? So this is something, let me just plot that, and that makes it easier. These black dotted lines or dashed lines, these are the controller bounds, right? So this is basically protecting your equipment or your process. And this is very, very important to understand because this is one of the main limitations you have in practice. If you are hitting one of these bounds, you cannot further maintain the set point. You can nicely see that here. So this is, in this case, the airflow set point. So it goes up, hits the upper bound, and you see that suddenly there's a difference between set point and controlled variable. And that is, of course, because the controller wants more air, but reaches a maximum. So there's not enough air going into that tank. Yeah, very important. So if you plot that this way, it's relatively easy to analyze. Okay, so we have a difference between set point and controlled variable. This is the reason. Yeah. So these bounds are very, very important to look at. They have all kinds of meanings. In this case, that specific case, the maximum airflow is very often defined by the maximum airflow per diffuser. So that is a spec these diffusers have that you are not impacting the equipment itself, right? So the lower bound, there are two things. One is minimum airflow for mixing, right? So that the sludge is not settling. And the other one is minimum airflow per diffuser. And that might be very, very critical because ceramic diffusers may actually be damaged if you go below. Yeah. So very important, that protects your equipment in this case. Good. So just a summary. So the manipulated variable bounds cover process and equipment limitations and protect against integral windup. Not enough time today to go into integral windup. Very important topic as well. Also important, just from a conceptual understanding, is if you are hitting a bound, that controller is not active anymore. It's just running on a fixed value. Overcoming manipulated variable bounds must be done outside the controller, which means you can retune whatever you want. There is no improvement in performance, right? So just the exception would be if the controller is tuned way too aggressively, that you have an oscillation, and that's the reason that you are hitting the bound. Let's say continuously hitting a bound like you see here. You cannot solve that by changing the tuning. Very important so that you know what causes it and how can you overcome it. A lot of discussions are, oh, well, that is the performance is not good enough and we have to retune. In this case, you can tune whatever you want, no change. Yeah. So let's. This was focused on a single control loop. Yeah. What we now look into is how control is implemented at a real wastewater treatment plant. So, and what you typically realize if you start digging is it's not just one controller. It's typically in a cascade setup. In this case, that's an ammonia-based aeration controller. So we have an ammonia controller in red. So you have a set point, and then you have the measured ammonia, and that controller calculates a DO set point, right? So one controller calculates the set point for the next one. So this is DO calculating an airflow set point, and then the airflow controller calculates finally a valve position. At times, you even have a fourth control loop, which is a valve positioning controller. Yeah, so you see that's quite a cascade. Yeah. So what we didn't discuss yet is that you very often have multiple aeration grids. So even within one basin or one train, you may have 5 of these cascades, right? Because every single downcomer has an automatic control valve, right? And then you have multiple trains in parallel. And what we didn't discuss yet is air supply control, right? So this is purely air distribution. There has to be a certain pressure pipes so that you can properly distribute it to the different grids, right? So it gets more and more complex. It's not just one cascade, it's cascades in parallel, and then also combinations between air supply and air distribution. Yeah. So what you see here, so that you have the air supply, which is the blower control, typically based on pressure or airflow, total airflow. And then on the right-hand side, you have the air distribution control, and that is basically dealing with a lot of equipment from valves, pipes, and then also diffuser distribution, right? So very important. If you think you automatically get the air where you need the air, that is not true. In all our aeration control projects, we find that equipment and process are heavily limiting what's going on. In between air supply and air distribution control, you very often have most open valve control. This is basically trying to help balancing supply and demand. Yeah. So let's jump into control system design. So this is what we do with clients. Yeah. So the first thing really we do is we sit down, we have a workshop, and then we discuss how to prioritize process goals. Yeah. And I will go through an example for ammonia-based aeration control to make it easier to understand what I mean by that. One of the main design steps is to translate the process goals into control goals, right? And funny enough, you can actually achieve a process goal with a very, very bad controller performance, or vice versa, right? And the best solution, I would say, is if you can align process and control goals. And again, so I walk through that in a sec. Then you should identify process and equipment limitations. I will give some examples as well for ammonia-based aeration control. And then you start putting together the control structure. So knowing what you want to achieve and also knowing what the limitations are. Setting bound is an essential step in that, and then in the end you tune the control loops. Yeah, so that is a typical procedure we apply in our projects. Yeah, so let's look into one example for ammonia-based aeration control. So let's start with oh, the title of the slide is wrong. That should be actually design, and that is process constraints. Yeah. So one of the main constraints coming from the process itself is a kinetic constraint that if you are reaching a DO concentration of about 2 milligram per liter, then more air is not helping. Yeah. So if you are increasing the DO, let's say into a saturation, that is not helping the process. Yeah, very important to understand. An ammonia controller is very powerful going down. So if you basically drive the DO down to zero, switching off the air, that means you are switching off nitrification. On the other side, if you have an activated sludge system, at least, if you're reaching about 2, nothing is changing. And 2 means 2 in the least favorable section of your aeration basins, right? So that means if you have lower DO concentrations somewhere, increasing the DO set point would still give you some additional performance. Yeah. Another constraint often overlooked is a limitation. So that is for ammonia-based aeration control, the mass of organisms, and for ammonia-based aeration control, that's the nitrifiers, right? Very often, the the performance of nitrification is limited by the mass of organisms nitrifiers in your system, right? So the mass of nitrifiers depends on the average load and the ammonia removed in your system, and you can basically adjust the sludge retention time to accommodate that. Yeah, so very important to also understand that ammonia control, if you are not maintaining a set point, you have to go outside and increase or decrease the sludge retention time to make it work. Yeah, and then of course that is limited. The SRT maximum is limited by your clarifier performance. So that means you cannot go higher than a certain mixed liquor concentration, otherwise your clarifier will fail. The last one is sludge settlability, and that defines minimum airflow for mixing. That's something where we run into all the time with ammonia-based aeration control, right? So also a limitation you have to be aware of, and that will not allow you to get to the full benefits of that control solution. Good. So what about equipment limitation? Right, so we discussed briefly air distribution networks, so pipes, valves, and then for diffusers, mainly the distribution, but also the specifications. Right, so blower capacity is clear. So if you are reaching the maximum, there's not more air you can deliver. For ammonia-based aeration control, very tricky is actually the possible turn down. Right, so the lower end, the minimum, because that is limiting what you can achieve in terms of energy savings. Yeah. The last one, diffuser specifications. That's again airflow per diffuser. I mentioned ceramic diffusers already. You have to make sure that this is maintained. The way we design that is a more holistic view. What you can see is a Simba model for an aeration system we looked into. So very detailed with blowers, valves, pipes, of course, and then diffusers, all fully dynamic, including temperature and so on. Yeah, so highly dynamic, highly complex, and we use that more and more with quite interesting results. So let's go through that step, comparing potential process goals with control goals, right? So let's start. So that is specifically for ammonia-based aeration control. One of the main goals in terms of process we hear from our clients is typically, yeah, we want to save energy. Yeah. So a potential control goal or translation into control goal could be vary aeration intensity to maintain an ammonia set point, right? And this is to reduce nitrification and save aeration energy. Sometimes they say, oh yeah, we have ammonia breakthroughs and we actually don't want that. So we are not feeling comfortable with that. So we want to reduce ammonia effluent peaks, right? And here you see that is a different control goal. In this case, I say, okay, increase the mass of active nitrifiers by aerating a swing zone. Yeah. So instead of changing the aeration intensity, I am switching on and off a swing zone. Increase total nitrogen removal, and you see that there's a whole list of process goals, and important is to put priorities in. Yeah. So if you want to reduce total nitrogen in the effluent, lower aeration intensity to maintain ammonia set point, basically it's the same, right? And the explanation here is favor simultaneous denitrification when possible. Yeah, so if you are fulfilling your nitrification requirements, use the rest of the capacity to denitrify. And then improve BioP performance, lower aeration intensity to maintain ammonia set point. So you see it's again the same control goal. So you would reduce nitrate, recycle into the anaerobic zone. So if that would be the BioP performance would be the highest on the priority list, I would design a different controller, right? So the order, the priority list is very, very important to look into. Yeah. So these discussions you have to have with your client to understand what they actually are interested in. Yeah. And then depending on what is most important, you actually have to design your control solution. As a constraint, typically at the very end, you hear, oh, we also have to maintain our effluent permit, of course, right? So this is your safety margin you have to put in, and that will be reflected, for example, in this case, in your ammonia set point. Yeah. So very important to really write that down, and it's quite an interesting exercise, and that requires a lot of discussions, I would say. The exception here, so all three could be done with the same ammonia-based aeration controller, except that one in the middle, fighting ammonia breakthroughs. This requires different actuators, so not aeration intensity that is on the swing zone, right? So if that would be the focus or the main priority, that would be the one to work on. Okay, so let's look into control structures, right? So that would be then, so we define what we want. We decided, okay, so we want to manipulate the aeration intensity. So how is the control structure looking, right? So we typically recommend a very straightforward cascade implementation. So basically ammonia measured at the end of the aeration tank on DO, which is depending. So if you only have one DO probe, then typically you have that about 1/3 downstream. Yeah. And then you have the airflow control that is per controlled section, right? So very straightforward cascade. There are other implementations out there. So one is called direct ammonia-based aeration control, where the ammonium controller is going directly on the valve position or the airflow loop. I clearly not recommend that. One thing is it's very difficult to tune, and it's also not protected against high ammonia load. Yeah, so clearly not something I would recommend. Feed-forward feedback combination, you see that popping up everywhere. I would say typically not required. It increases cost mainly for sensor maintenance and quality control because you have much more sensors. And you also have to keep in mind that you need to do model maintenance. So that's a lot of additional work, and you have to look into the additional savings you can achieve by going more complex. Again, keep it simple. That makes it much more robust, and you very often have a much, much higher payback if you keep it actually simple with a minimum of sensors. Model-based, ammonia-based aeration control, due to costs and complexity, rather something for larger plants. And again, even for larger plants, I would say keep it simple. Yeah. So feed-forward control makes sense if there is a problem with how fast the system reacts to changes. So that is the big advantage of feed-forward. It can react faster. If you don't need that faster, try to understand what is impacting performance and then fix that. Yeah. Good. Control system design. We try to do, we are using a holistic model supported design where we basically have the 4 parts of a control system. So the process we model, the sensors, the control system, and the equipment, in this case, the whole aeration system. Right, and then gray, you can also do cost calculations, dynamic cost calculations. You can vary influent in temperature, and you could even model equipment failure. So that holistic model-based approach means that you have to have a very detailed model of your aeration system. In this case, it's with blowers, with pressure and MOV control in this case, main header, basin header, and then the drop legs, manifold, laterals, diffusers, and then you have DO and airflow control. And of course, it's also connected with the process model to calculate or estimate the oxygen demand of the process. Good. In terms of commissioning and operation, really the key here is to visualize, right? So that it starts with sensors, plot the results of your QA, QC, plot the controlled variable itself, make sure that you are monitoring your equipment, also visualize. For the process, it's very important to fully understand what's going on, if the process is somehow limited, right? And then the focus of this presentation is controlled. So clearly make sure that you monitor your control system. And again, plotting is, I would say, the most important thing. And I hope I gave you some ideas how to plot in that presentation. Some non-technical issues. First thing is get your operators on board from the outset, right? So if they are not understanding what's going on, that will never happen. Yeah. I would also recommend increasing complexity step by step. So start simple. If you want to do ammonia-based aeration control, make sure that your DO control system is working first. And then do that additional step going into ammonia-based aeration control and then into sludge retention time control as well. Yeah. Start knowledge transfer and training early. We now recommend doing virtual commissioning. So you can start with knowledge transfer and training before the new plant is built or your new control system is fully implemented. Right. So very, very important that make sure you have a smooth commissioning and startup of the system. Something I like to mention is incentive systems, right? So you have to make sure that all the involved operators and instrumentation techs have a clear incentive to make it work, right? Sounds trivial. I hardly ever saw that properly implemented. And I would recommend figuring that out before you actually go into commissioning. Good. Take-home messages. Benefits: clearly control gets more out of your treatment plant. And this is done by dealing with the inherent dynamics of a wastewater treatment plant. Control can reduce resource consumption, so energy, chemicals, and so on. But it could also help increasing robustness. Right, so just keep in mind these are two different process and control goals, and you have to make sure that you find the right control solution for it. Smart controller design: start with a very clear objective. Do that workshop in the beginning. I hope that the procedure we apply helps you as well. Translate process into control goals. Understand process and equipment limitations, and basically use a model to figure out what that is and what impact that has on your performance. For operation, train your operators and monitor sensors, process, equipment, and the controllers, right? And visualization really is key. So make sure that you have your plots set up before you start that. With that, I'm happy to take questions.